need actually. Sorry.
For most modules, you guys have exams.
Yeah, the other three I have exam.
You know what's horrible? If for OS, your coursework like is due in on the 18th.
Yeah. We're gonna talk
started
about it.
We started doing it.
No, it came out yesterday.
My friends like it. Like
Seriously?
I have friends which don't have any exams right now. They have any talk right now, so they can do it.
Like back home, like we start assignments like 2 days before they're due.
Okay, that's normal over there.
Exactly, very good stuff.
That's like doing my flexible stuff like 2 days before.
Yeah. I mean,
But I did like my OS coursework. I finished doing it like on the day itself because
yeah. It's
I
like,
was
the
doing
thing,
other stuff.
the thing is, like, with these courseworks, they always get extended, that's what I've noticed. So,
Really?
why bother? This got extended by 2 days.
That's because it was a mistake, not because.
Well, still, I mean, there's something that comes up, like every assignment, every 12 now, it's getting extended. The West got extended,
I don't know.
network system got extended. People are complaining how, like, they had a project to do and stuff, so they're looking for 2 days. But it actually did help, though. This was like, the coursework honestly wasn't that bad. Let's not talk about that.
Trying from the edge, which is weird. But rationalization's fine. I feel like this is I don't know. I don't think it draws it at all. Yeah. Like it does it to the blue one. And if I reduce this to like that.
What else do you have going on for
I have what's booked your Thursday? Quiz?
today?
Thursday? Faculty. Traffic. Yeah, but distance. So it's not same as yours, but I have no idea what right. Yeah.
That's what is
That's what I love my
research project. What's that?
well, for the time being, I feel like write a summary of like why papers, fairly long, 100% cover, so one would also pay. And Tobias is my
Is he? How is he? Like,
oh, he's really cool.
oh, okay.
The next level will be implementing like the masters and mapping.
Oh wait, you have to start from there.
But that's just me, like, it doesn't really work. It doesn't work. Wait, it's wrong anyway, so.
Why? You were meant to like see yourself, right?
Didn't know that I reached it. I didn't know that I moved to 1 minute clock.
Get it from track. You know how to get it from.
Some of the other things you get to do take time to wait by those some of the
Triangle is the area that is so far.
Yeah.
For a general polygon, he said we could get that before the
Yeah, but
She's saying you triangulate the polygon.
let's get started a bit earlier. 3 minutes we saved, which I will use to recall a bit what I didn't properly finish last time, because it just takes a bit longer than I thought. So I will just go over this. This is recap. If you already understood it, you can use the time for other stuff. Oh, microphone. So that's the rendering equation. It tells you if you have a point somewhere, what's the amount of radiance, so this thing which corresponds to your natural understanding of bright or light, just with colors in it. If you have this function that tells you how much this is at some position in some direction, this is a composition of two things. It's the light being emitted already, which is non-zero only for light sources. We discussed that this can vary over space and can vary over directions. Don't forget the difference between a projector that just sends in one direction or a light source that just sends everywhere. This can be very small or it can be extended. All of this will be supported if you have something that is based on the rendering equation. No light sources, no point lights. Don't think in this way anymore. And you have another component, which is the reflected light. It's the entire other part of the equation, and it's an integral, in particular integral over the entire spherical domain sitting above this very point x. And it's made out of three components: the BRDF, the incoming light, and something called the geometric term. So I said this is what you want to compute. I explained that this is what is being emitted. All this is the reflected light. You see those little images, so try to match these if you still want, didn't understand from my explanation. And this has three parts. So the most complicated part is really finding out at that very position in some other direction of the incoming light, what is the nearest point along that direction. So in the drawing, it would be this point sitting there on the sphere. Could also be no point. You remember this in ray tracing. Sometimes you hit nothing, so then you cannot compute it, or you have to define what's the light coming from nothing. Black is maybe a good idea, yeah. And then it goes into the other direction because it's this point sending the light exactly in this direction from which you're looking at it. I discussed that there's the BRDF, which is a function that is varying over space. And when you fix a point x, there are two angles on the sphere. And this function basically encodes the relation of how much the light that would come in from that direction incoming would be translated into something outgoing. I gave examples of two important BRDFs. One is the diffuse BRDF, which gives equal weights to everything. So it doesn't matter where you put the light, unless the angle changes because of this. Everything will be the same, and the other extreme is a mirror. There would be a Dirac function, so it would basically select only one very particular configuration. If I give you one input angle, a mirror only gives contributes light from exactly one other direction, which is the direction that is exactly the mirror direction. It would be zero for everything else. Yeah? And I'm motivated that this is complicated to solve and so forth. Yeah? So now's the time to ask questions on this one, because we're going to base on that, because I just explained what it is and I didn't give you a way to solve it, and today we talk about a way to solve this. So questions on this formulation of the rendering equation? No, good. So did I really finish? We went over all of these things, and here I ran a bit out of time. Yes. So what I also wanted to say is it will be very useful, this formulation of the rendering equation, because there are certain special effects that you all want your renderer to do, which is motion blur, anti-aliasing, such that edges appear nicely blurred and not jaggy like this one. Motion blur, everybody knows, when you have a longer exposure and you have this one scenario at night, this would be sharp, this little telephone house, and the bus would be along the motion direction blurred. You have depth of field, things which are out of focus, they should be blurry in a specific way, and you have those very complicated light transport things that depends on the colors. And if you really understand the rendering equation, you can really generalize it even a bit further, and would also support all of these effects. Yeah. So if you're able to write up some to have a solution to the rendering equation which is so general that it includes these effects, well, you get all of them, and then you really are complete. Then you can make movie quality like pictures, including motion blur. So to recall how motion blur works. If you have time going and you have this simplified drawing of the bus, all that is happening that those images at different points in time get averaged, and enough of things being averaged, you get something being smeared out along the direction of motion of the bus, and if you sum them up, you get this. Yeah? And that is something that you can write as another domain of integration, where you just say, okay, instead of just having my points x and my directions in which something has a certain brightness, I'm also integrating over time. Yeah? So you're not just saying, I have this very point and it has this brightness, but you say, I have a certain brightness at a certain moment in time. So you can generalize it. This could be a light which is maybe blinking. So maybe you saw this before. If you have a light blinking and you take and it's motion blurred, when it's during the shutter interval, so during the time while you're taking the images blinking, you get like isolated points, or maybe it's constant. That's the easiest thing. But everything can depend on time. Even the brightness if you manage to find a material where you can change the brightness over time. All of this you can write time dependent. This is important because this now would say if something, if this point y, what I see in a reflected direction is changing, then this value will become different. And that's what's happening for the bus. So for the bus, you see the background, you see the wall, and the bus was moving, so this function was changing. So these values are changing, and you're integrating them all up over time, and this gives you the appearance that the bus is being blurred. Yeah.
How do we represent we need a time representation of
Yes.
the geometry as
Yes.
well? Do we
This is,
discrete, or
yes,
do we have
well,
multiple?
this is a question of how you, this is the same question that you would apply to all the other stuff. How do you represent things? You have different levels. Of course, you have your modeling package that in some way has to have a support for expressing how things move over time. But imagine you have this. Maybe you have a flow vector at every vertex or something like that that just tells everything goes 10 to the left. Yeah. Once you have that, it boils down to the question, how do you get your vertices moving into something like this? And as I told you, this very likely you will solve with ray tracing. So if you are at x, finding out what y is and what this value of this function is, your ray tracer will do, and it will be a time-dependent ray tracer that takes a time coordinate and has to deal with the fact that now your polygons are moving and the function should change. Yeah. But how do you do it in the end, how you solve the entire thing? Yes, all I want to say is just another integration domain with another variable, and all of this you don't fully have to understand. I think now it's only about understanding that there are new coordinates that you can introduce. In this case, it's time, and it's different for every frame. That will just make it more general, and everything is always an integration problem. The same thing for anti-aliasing. If you have reality here, it's very sharp, infinitely sharp black boundaries of that object. If you trace just a single ray to every pixel, yeah, or you set up the rendering equation to solve exactly what is L, X, omega at this very single sample position, you will get something jaggy, because either the ray hits the object, then it's black, or it doesn't hit it, then it's white. Yeah? But what people usually want is this thing to be anti-aliased. Yeah? So intuitively, you send multiple rays and you're averaging them, and you get a nicely blurred copy of this. This looks, of course, bad because it's so little pixels, but in a real image, this is going to look much better. And this, again, you can write as another integration domain. So instead of just saying I take the value of the brightness for a certain pixel to be just the brightness that you get at the position of the pixel in a certain direction, you're saying, okay, I'm also integrating over the entire area of the entire pixel. I'm weighting those things that I get at those positions, and I basically take the average of all of these things. So it's another integration domain. In this case, it would be the pixel coordinates, so you're integrating over the entire area of the pixel, and Monte Carlo ray tracing will also be able to handle this. And always you give different weights to the things that you find. So when you're integrating, it is favorable to not just give everything the same weight, but give slightly higher weights to the center of the pixel and slightly lower weights to the other ones. And there is a family of things that you can use, and all of them would give you different results. Yeah. So if you have many, many white bars and many, many black bars, and you do this, you get different results. I think you all agree that this looks a bit nicer than something like this over here. Yeah, and this is just choosing the proper anti-aliasing. Same thing for depth of field. Let's recall why this is. If you have a aperture which is just a point, and you're somewhere on the lens, and you have a point where this goes through, if you have one black object, it's mapped to another black object, and you will get just a single output. But what in reality happens is that these apertures do have a finite size, so it's not all just going to a point. And then you could do projections equally well to another point on your lens, which would give you a different image. Or you can do projection to another thing. So basically everything in the lens results in a different image, and same as you do over time. If you average all of these images, you will get something which is blurry in a very specific way, and this is depth of field. And this is, again, another way of integrating. So instead of saying your pixel color is the pixel color when I do a projection to the center of my center of projection, as you have learned, you can just take all centers of projections that you can, you integrate over all of them, and this will again give you an image which is blurry in a specific way, depending on how much this area is over which you're integrating. So if you make it very small, you get back to your pinhole projection, everything will be sharp. If you make this area larger and you integrate over something which is even more large, you will get something more blurry. And again, there is a little function that would weight certain areas more. So maybe if you're outside there with your camera, things get darker, and if you're more in the center, things are brighter. And you can design lots of lens functions. You can have things which are rectangular, you have things with 5 edges or circular ones, and depending on these, the image will look different. So you can basically simulate a true camera with this. Again, you don't have to understand all of the details. I just want to convince you there are lots of things over which you can integrate, and this logic of integrating over many things to form an image, they do not just they do not just explain how this works in space and in direction, but also over time, over the aperture, over the lens, over the pixel, all of these things. And it gets even more exotic. In the beginning, I told you we're ignoring all the wavelength-dependent effects. We're ignoring fluorescence and all this time propagation and so forth. But in the end, if you want to do your computation, you have to do it for a certain wavelength, because there are things which are wavelength-dependent. So I showed you the laws of refraction with like these Snell laws and so on. If you look this up on Wikipedia, you will see that the index of reflection depends on the wavelength. Yeah? So if you have a piece of glass, and it gives you a certain index of refraction, and you render it with one wavelength, so let's assume some single fixtures wavelength, you will get a pattern like this, because all rays are exactly sent into a certain direction for a certain wavelength. If you had done it for a different wavelength, you would end up somewhere else, because the index of refraction depends on the wavelength in reality. Yeah? Something that you did not simulate in your ray tracer, you just said IOR is, I don't know, 1 over 1.3. In reality, it would have been different for red, green, and blue if you want to simulate something like that. So then what people are doing, you can just take then, you can take your ray tracer and you can take different IORs for your different wavelength, and what you will get then sounds more correct, but it will basically give you just 3 copies of things, because one wavelength will give you this IOR, so it will give you this pattern. The other wavelength will give you a different IOR, it will give you the green pattern, and the other one will be red. And this will not be as what you would expect to see down here. And this, again, you can write as an integral basically over all continuously many wavelengths that you can imagine. So instead of taking a single one, you're also saying, I have some spectral coordinate, and then it would be the integral over all the wavelengths that you can imagine. So if you want to get the color red, instead of taking the red IOR and just running with the red IOR and doing this, you basically go over all the wavelengths you can imagine. There is a function that tells you how much the wavelength is contributing to the red channel, and you're solving the rendering equation for this. And if you integrate them all up, you get a nice continuous rainbow, and you can also simulate these effects. So I think I gave you like 5 or 6 dimensions over which you can solve this integration system, and if you do all of them, you get like motion blur, depth of field, anti-aliasing, spectral rendering, and you don't need to understand all of these details, you just need to remember all these are new integration domains, and they are good for getting certain visual effects, and yeah. Some are related to time, some are related to the aperture, and this one is related to wavelength, yeah. I think you can imagine, like for red, that this thing will be high, so you are more interested what the light is for a certain wavelength, which is more associated with red. Yeah. So, but it's not like selecting only a single wavelength. So what your monitor sends when you turn on the red channel is not monochromatic light of wavelength, I don't know, red. Yeah. It's a distribution of different wavelengths, and this thing is encoding this. I hope you learned a bit about this, how in image processing and in sensors and so on. If not, others can explain this better than I do. It's just here important. Instead of taking red, green, blue, or a single wavelength, you have to think about it as if you go over all of them and you solve an integration where all of them are contributing. Yeah. So the big picture, which I couldn't finish like last time, is rendering is solving a very large integral equation. It's very large in the sense that you do not only have this, which is the classic rendering equation, which sets up this point and then Lx omega, and then it's recursive and all of these things. But on top of that, you have time, you have aperture, you have color, you have pixel. And then you get an integral with 1, 2, 3, 4, 5. And the 5th one has infinitely many inside, yeah, because it can bounce as often as you want. And that's what you're going to solve. Yeah? And sometimes people forget about this. And that's really cool. This is what the movie industry is very interested in these days. Yeah, so people could do this to some extent, and then it wasn't so sure because it's already very expensive. But what people like a lot about this is that there are techniques to, for example, get skin very accurate, because the skin tones of a human, this you can only do if you do the color very well. Yeah, or people use motion blur excessively in an action movie or something. Or without motion blur, this will always look like soap opera. This is not what you want. So then you have to do this properly. And if you can do all of this, this starts to be really making even more sense, and that's why they use it in industry.
If we wanted to model a complex camera with lenses,
yes.
Would I take the lenses and model them as geometric objects?
You could do both, exactly. So some of different things here have different amounts of reality. This is a very good, almost philosophical question. This thing, in reality, maybe I should have put it here and have said this is an abstraction. How much you say this is aperture, or it's maybe actually really geometry, because I can also model all of this with glass and everything, and then I can get the same thing. There's no way I can model time by putting just boxes in a certain arrangement. That is a very different domain, yeah? But you are right. It's just more efficient to make certain simplifications here to say I have a simplified aperture model that just says instead of having a point projection, I have a projection where everything just goes through all the points, maybe in some disk arrangement, and then you can be more efficient. This is just some semi-analytic way, so to say, where you can partially do some things and help the entire system a bit. But you're totally right. If you want to do your ray trace in such a way that you really like put random positions onto your sensor and you trace your rays through this, you can do. It will just be even more crazy expensive, and people usually go for this or more advanced versions of this instead of like modeling your entire Nikon and putting it in your scene and then just looking through. But in theory, you can do. Like the theory, it allows you. But not for the others. Yeah? So there's no way like in color or time. This is just different quantities. Yeah. So physically based lighting relies on solving the rendering equation. The complete solution to these equations are not tractable, so simplifying assumptions need to be made. And you need to be able to describe the reflectance properties with materials. This should have been new in the last course, so all of these BRDF things, that's an important part of theory. And you can also consider time, pixel, length, and spectrum as other dimensions on which the rendering equation is defined. Yeah, so that makes it even more attractive to find a solution that really works in this and not some simplifying assumptions as we have made before. Yeah. Okay, so questions on this, because then I will switch to how you actually solve that. Good. So yeah, the solution to this entire thing is Monte Carlo path tracing. And what we're going to see today in this respect is how to solve integrals, because I showed you lots of integrals and integrals, so I do this intentionally because then I think you agree that you will not want to look into details of how rendering really works, but everything has become just a problem of solving an integral. There are different ways of doing this. There are analytic methods and numerical methods. I will discuss this a bit. There are lots of misconceptions about why certain things are done, so I will have my take on explaining you really why. I think on the internet you will find lots of explanations how path tracing works. It's a bit like sending random rays and then averaging. I think it's easy to program, but really understanding why and like so assessing the technology, why you do certain things or why you enable a certain function or maybe don't do in a different condition. This you will only understand if you really understand it in the way I intend to explain and not just superficially. So we will really see it on the level of solving integrals. And then I will show you in particular how to solve the rendering equation using Monte Carlo after we've seen what this can do in general for solving integrals. And there are different strategies because this one will be slightly noisy. That's technically called variance. And you want to get rid of noise in your image. So there are techniques called variance reductions that by using just more organized ways of randomness, because Monte Carlo involves randomness, by doing more organized ways of randomness, you can improve. Or there's importance sampling, which identifies, so to say, in this very high dimensional space of all these integrals, at least 5, and then another infinitely many. In these, there are some more important spots, yeah? And like identifying them, like in the beginning, is an option for like focusing your computation on the important parts. And that's the technique called importance sampling, and that's usually in all the modern path tracers, and it won't do properly without. Okay, so last time I already asked, so how would you solve this integral? What are the basic two options? So the German colleague's not here because he last time explained this already to an extent. There are basically two methods. You could either try to do this analytically, like you did in school, or you could do this, and that would be accurate. So if you can solve this in closed form and you can compute me the value, maybe you can. For a very simplified scene that just has a single plane that doesn't have any light or something, or just a plane and a parallel other plane with the constant amount of light, maybe you can solve. But for anything real, there's no chance. So what people usually do, they do something approximate. And these are numeric, and there are 3 different alternatives. There's a more straightforward one I will explain, because it's almost correct already, but just has some drawback that makes it not practical. Not practical. And then there is Monte Carlo, an extension to this. Again, it's a numeric method, and yeah, but both are approximate. Just redundant. So again, here's the little tree. What we're trying to do is integration. You could do it analytically as you did in school. What we will do is numeric. There's something called cubature, which doesn't really work. It's a bit like a dead end. There's Monte Carlo, which puts randomness in, and there's quasi-Monte Carlo that removes, again, a bit randomness to find a trade-off, and this is usually what you have today in the movies. Yeah. Okay, so let's just recall what analytic would be. It's the thing that I never could get right in school, and tell me if this is again something where I made some error, but it's these things, yeah? When you have x and you want to integrate it, it's a half of an x squared and so on, or you have sine and it's minus, and this is already where it ends for me. If you can do this for the rendering equation, we should talk, because that would be some fundamental scientific achievement, but everybody, I think, agrees you can't really do. Yeah, it's difficult for a function that we have, because how would you do this? It's impossible already, because the input is not analytic. If we have very simple analytic shapes like our spheres, maybe it would be. But now when you come with a bunny and you have maybe the sun with all its complexity and wavelength and all the configurations, this is not something you want to do analytically anymore, and it maybe doesn't even have. This is maybe the interesting analytic result, that it maybe cannot be integrated if you have very sharp, infinitely sharp boundaries in your polygonal geometry. And you can have, like a cube, it like infinitely, I explained this last time, if a ray just moves, you have an integrand which with infinite variation, they say, so you just move a little bit and everything totally changes, and that prevents and defies all the analytic solutions, I think. And besides being impossible, it's also difficult because it has the recursion in it. So this is something that you usually don't have in school. Yeah, so the f of x doesn't appear on the other side. I also don't know how to do this. This is another reason I wouldn't want to do it. And it's also difficult because it lives in the spherical domain. I explained this before. This maybe lives on the line, and integrating there you learn in school. Maybe in 2D this is still something you learn, but on the sphere you have even more complicated definitions. And yeah, this is not where you want to go. So some analytic things works. I was hinting at that, so don't quote me on saying it's impossible. There are certain things. So if you have, for example, a single rectangle and you want to know this is the only thing in your scene, and you don't have visibility, and you don't have spectrum, and you don't have all the stuff that I just described. The theory, sometimes there are analytic solutions. So if you want to know this, if you really want to get the integral of this, you have to recall what spherical angles could be defined in. So you have this spherical coordinate system with latitude, longitude coordinates as they are on Earth. And the integration you can just do, I think it's separable. So you first integrate over latitude, then you integrate over longitude. And if you can do this symbolically for a simple enough expression, you have a chance. So integrating a function like this that just says, okay, it's a constant if the angle, like the latitude, is between 2 and 3, and the longitude is between -1 and 1, and otherwise it's 0, there are chances of computing this, yeah. But I won't go through those symbolic exercises. Sometimes you can use it for a little game, for example, as an approximation. That's another story, but for Monte Carlo ray tracing, this would be all too cumbersome, and we also don't need it, yeah. So again, I would like to ask you to forget a bit more about those spheres, and the real abstract problem is how you should see it, or how I think didactically it should be seen. You have some domain, omega, large scale omega. It's very abstract. Here it's just a square, but this is how I can draw it in PowerPoint. You have coordinates in it. They could be very high dimensional. This is 2-dimensional because I can only draw 2-dimensional. And there is a function defined here, which is f of that omega, and it's just the value that the function has. So if it's dark, it has a low value, and if it's bright, it has a high value. This could be the incoming light, or the incoming light times the BRDF. It's this thing that you're integrating over in the rendering equation where the integral is in front of. And this we're interested in. So in this example, I want the solution f. That's the integral over this entire thing, and I just claim this is 0.85. This is just, if you integrate this up, you can imagine this might match, because this I count as 1, this I count as a bit less than 1, and if I integrate this up, it's almost 1, just a bit less than 1, because there are some parts which are darker. This is like in the ballpark. So if you're able to do this as robust as you can, such that it carries over to this infinite dimensional business, you can also solve the other one. Yeah. So the other branch, which I said, which is not analytic, is what your fellow student just said last time. The simplest approximate solution is numeric integration. So you take your domain, however you do this, if it has 20 dimensions, you can also do this in 20 dimensions. You decompose it into little elements. And this is exactly numerical integration. I think this you know from school. So if you have your 1D function, if we just go back, what it does, it takes maybe equidistant points, it computes the value of the function, and then it just, so to say, assumes that the function is constant on that little interval, yeah? that makes you, that allows you to compute the area under this one, and then you just sum the area of all of these blocks, and that approximates the integral. It's not correct because this one is, for example, larger than this one, so you're here, I think, underestimating it a bit. In other cases, you're overestimating it, and so on. But if you make those blocks smaller and smaller, you get closer and closer to the true value of your integral. Yeah. So if we do this for our example, let me know if it's not correct again, but I tried to do it here. So I count these as 1. And then there are other little cubes where when you pierce through, in whatever dimension this is, the value that the function has then. So I count this as 0.2. These 3, they were hitting that spot. This was hitting the slightly brighter spot. You sum them all up, you get to 13.3. There are 16 squares, and you get a value like 0.83, blah, 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 which is not that far from the 0.85 that you would want to have. That's numerical integration. And this is what is, so to say, yeah, this is the typical like engineering computer science answer, how you could maybe solve such integrations, and that's already not so bad. So if you do this a bit more refined, as you maybe know from school, if you make those blocks smaller, this would be smaller cubes or hypercubes or whatever dimension this thing is. You make more and more of them. You can again count. I was too lazy to put like white squares, so I ran out of time, and I also don't want to list all of this, but this is 64 squares, and I think I computed this is 54.2 in here. Yeah, and you again do the math, and luckily I got closer. So that's not just luck in the limit. I hope you agree that when I take more and more spheres, they get smaller and smaller. I do less and less errors, and this value, which is the true analytic solution, maybe I just claim it is. Yeah, and then it gets closer to this one. Yeah. In fact, I just did this first, and then I just set it 0.85 in the end. Who knows what it really is, but I hope you get the idea. Yeah. So this carries over. So more formally, if you want the value of the integral, like the large f of omega, that's the integral over this. Just do a sum over lots of coordinates where you just take them in some regular arrangement, whatever high dimensional this is, be it 2-dimensional or it even works on the 1-dimensional real line. And to find the integral f of this function, you decompose it into n as small as possible cubes. Of course, you have to do more work. If your n is very large, you have to compute your function very often. So if you have 1,000 quads or 1,000 cubes, you send 1,000 rays. Because remember, the function you're integrating in it, it had this Ly, which requires ray tracing and so forth. So it's costly. So at one hand, you want this to make it small, as many as you can to make it accurate. At the other hand, it also is costly. And you evaluate f for each of them. So you call these guys typically sample, and in the end, you're averaging this, and this gives you a result of your rendering equation. So you could go now and take just your 7 plus, I don't know, 10-dimensional thing, decompose it into little cubes, compute it for all of them, average. It's a very simple algorithm, and it would solve it perfectly in a sense. Yeah, if you manage to make those cubes smaller and smaller, it would do it perfectly. Sounds very simple. So is this already it? Yeah, very simple method. So let's recall, to get this Lx omega O, so you are somewhere and you want to know at that position and with this incoming light, no, like at this position what basically comes to the eye. What you would do, you would subdivide the hemisphere sigma above x, so you have to imagine that's your little integration domain here on which this is defined, into n strata, this is how you call it, like this is little pieces of your surface. Imagine it's maybe 100, like 10 in latitude and 10 in longitude or something like that. And you have to evaluate the integrand then. So evaluating the integrand, f, the integrand in this case is this triple product of the incoming light, the BRDF, and the geometric term. This you can compute in closed form. This is just the dot product of two angles. This is your BRDF. In the worst case, it's your Phong with some exponentiation, but it's not complicated to evaluate. What's more complicated is this. This will tell you what's the incoming light. So once I see this, I have taken any of these 100 strata, I go into the other direction. I would have to find that other position and how much light it's sending, and that makes it recursive. But let's assume you could do this, and then you average and you're done. Yeah, this would be the most simple algorithm for this. It's even simpler than path tracing. You don't have to differentiate between reflection and refraction. You don't have to maintain a stack. It's even easier to implement in WebGL and so on. So this is not so bad. But there is one little problem with it. The final thing will not be so different, but there's one substantial thing in it that doesn't make it work well. So the L appears on both sides. That was one of the problems we had. Yeah? And for this, if you want to have Ly, which appeared inside, you have to solve another integral. So if I want to solve this guy here, I have those 100 bins for each of the bins. Yeah? For each of the bins, you have to go somewhere else. So this will hit over here. So here again, you have your 100 strata. and you have to know, to get this value, how much it sends over there. You have to integrate over all of them, so you will not get away cheaper. Then again, do it 100 times here, and for each of them, you have to do it 100 times more. So it's recursive. You know, I ran out of letters, but the Y turns into a Z, and then I had the Z2 and Z3, so this is just exploding. Yeah? In some way, that's the nature of reflection, so you cannot really avoid it, and it's not per se something that is bad. So recursion in CS, of course, can be very good. There are many recursive algorithms. That's not such a problem. And it also worked kind of okay in ray tracing, yeah? So if you remember this little ray tree, I think you remember, but because you had to use for your exercises, yeah? And it's splitting all the time between two branches, the reflection and the refraction. And if you go to def D, I think somebody here asked, okay, how is this going to explode, or how is this scaling? And here a bit more formal, if this is really only 2 rays and you go to def D, this is 2 to the power of D. Yeah? So that's already exponential, which is not so good, but it's somewhat realistic, because if you go to ray def 3, for example, so that's reflection, no, that's primary ray, and then a reflection and another refraction, which is maybe what you used in your exercises. This is going to be 8 rays for every pixel, and that might be doable. But if you see what this would turn into, if you just follow this classical cubature rules, where you always subdivide into something like 100 or 1,000 rays, this is impractical for solving the rendering equation, because now n with 2 is basically the minimum thing that you can have. And if you really send those rays, and you will not get away without it, otherwise you cannot get the integral of this other point. You have to get over all the points. You cannot take any shortcut and just claim this would be right. So if you had to do this already for the first point, already for here, you have to take 100 samples, and for each of them 100 again. So if n is realistically between 100 and 1,000, this is 100 or 1,000 to the power of 3. So for a single pixel, that would be 1 billion, English, US, I don't know, like it would be too much. Yeah? So for a single pixel, this is already too much. And not to talk about making this D, it's like scaling very, very unfavorable in the D for any reasonable n that you would have. Yeah? So how small can n be? You saw it in this little example that I showed you, like in this flat world. How small would it be? This is with 64. Is this quality already enough? If you imagine you have like a white piece of paper with these things being shadow casters on it, and this is what you're integrating over, it's really a question. But I'm sure that 1 or 2 is not enough. So like realistic is rather 64 to have a bit of refinement where things are. So no chance of having this like with 2 as you have for ray tracing, where it already is not favorable, and with reasonable n like 100 and 1,000, no way. Yeah. So the problem with regular cubature for solving rendering equation type integral systems is the course of dimensionality. That is, if you go to higher dimensions and you subdivide something regularly, no way. It's the same thing like when you want to store all the combinations of, I don't know, income, gender, height, and you want to sample this. At some point, you will need so much data, there is no chance that you will observe it. It's a bit the simulation equivalent of this thing. Simulating all the cells in some high-dimensional cube and then summing up, no way, because a high-dimensional cube has so many cells, even if it only has 10 on one edge and you go to a dimension 10 or anything like that, it's 10 to the power of 10, and it's not going to scale in any way. Yeah. And there's another way of seeing this. So this is what I was trying to do here with my hands. So in the notion of those slides, if you want to compute the value of this integral via cubature, there is one point, and if you really want to rely on this point being correct, for this individual point, you have to solve at a different point the entire complete other problem somewhere, and always recursively at that point, you have to do it again and again and again. So it's always just asking for too much to be, so to say, completely informed about what's going on to make the next step. And there is some form of approximation that you will need to make to ever have a chance of doing this. Okay, so at this point, I hope you would understand roughly how like this non-working algorithm works. It's not very complicated, and at the same time, you should also understand why it maybe is not usable in practice. So, any questions at this point? Mm-hmm.
If we have like mirrors facing each
Yeah.
other,
Yeah.
Then the recursion would be
Yeah.
like on itself. Like for calculating the L on a point, we would need other point. Yeah.
So where's the camera? I see it from somewhere else.
Windows.
Okay, I think it has to be somewhere like here, like you send the ray here and then it's just going back and forth. Is that what you're talking about? Okay, good. So yeah, but what's the question? In what the rendering equation would say, or how this method would perform, or if this is a problem, or just want me to discuss what happens in this thing?
Yeah, what happens?
Yeah.
So to solve one side, you have to know the other side.
Yes. So what the rendering equation would say, if this is really a perfect mirror, this would say, okay, the incoming light would depend on what you get exactly from that direction, and here it would say it depends exactly on that direction. So you could say this is a large integral, but all that it's interested is this value, because this is the y. If this is x1, this is the y1, so to say, and whenever you hit here, you would be again interested in this one, and then the x1 would become the y2 of some other x2, and you would always have them talking to each other. So in this case, I'm not 100% sure if it's even defined what it will turn into. I think you can imagine. So first of all, you have to have some emissiveness in it, so otherwise it won't have any color. So choose your emissiveness. Where does it emit something? Because if there's no emitter, this will be black, because it will already be black here. So you want one of them to be emissive at the same time? Okay. So then this is maybe LE at this location. What will happen? I think it will just bounce back and forth, and in reality, you can't have this in reality because you don't have a perfect mirror. That's why, so everything larger than 1 is not going to converge. I'm not sure about the 1, but all I can tell you, if it's smaller than 1, if any of them is smaller than 1, you're multiplying up a constant which is smaller than 1. And if you have a sum of things which are always powered, so you have 1/2 and it just goes down, this is converging, and that's all that I can tell you. And what happens for 1, if you write it down, I think it will be 1, because you're always just copying over the value up to infinity, but this is like a math philosophical thing. If you just have an infinite integral that integrates all of the time and never does anything except that infinity is 1, I don't know what the answer to this thing is. I can only tell you if all of these factors amongst are smaller than 1, this is something that converges.
Okay, but I was curious about, we can't really solve one side without having the solution of the other side, so we shall use some analytical method.
No. So what the cubature does is really, for solving this thing, it will first solve all the others, and not only this one, but all the others, which will all turn into many zeros all the time. So you have to first solve all the others in many, many other directions, and then there is one amongst them, which is this, for which you have to solve the other one again, and so you're just recursively doing this until you stop, which is a question of where do you stop, and that's the general question of where to stop, which we had in ray tracing. And well, I can discuss this a bit. You can stop at a fixed depth when you run out of resources, which would be 3, was 3 in your ray tracer, and here we will also not make it like very deep, because this is a rather artificial configuration in which this occurs. And so other solutions are that you look at the amount of light that it's still transporting. Yeah. So if you're integrating around, how you do it in practice is, if you're here, so I have to put the camera again. If you're here with the camera in Monte Carlo, what you will do is you will always look at how much the light at every bounce is still contributing to the camera. This is the logic in which you're thinking. You're not so much interested in the light, but you always know, while you're going deeper and deeper into your integral, you always know basically how much in here will really contribute to the solution. So it gets less and less, because this is always 0.9, 0.9. It gets less and less, and you're tracking basically that value. And once this has fallen under a certain threshold, you basically know that whatever you're going to gather here, this is not going to contribute much more. And this is a much more typical way of doing this. And so you will have to first understand maybe the full method, but there are, because this is biased, so this would change the result. Because I ignore small light sources, and this is just saying it can only contribute 1% maybe, but if you have a very bright light source, 1% of a very bright light source, it could maybe be a lot of contribution, and that is never sure. If I just shine a very strong laser at a very black surface, even if the surface is very black, it might contribute to the solution. So that's very hard to make it terminate. That's why people usually put randomization in. Instead of really doing this you can also do for your ray tracer. That's why I'm going to explain it. What you're going to do, you roll a dice, and you just compare this value to the dice, which is between 0 and 1. And then you have a certain slight chance that it will be so low that you're not satisfied with terminating, because the dice between 0 and 1, it could also be 0. Yeah? And then you have a very small chance, but not an infinitely small chance, that it will keep going on. And that would be enough to make it unbiased in the end. And then you always have, in the limit of running enough dices, you have a correct solution. This is like a randomized termination criterion. And that's what people are usually doing. But that already starts to be a bit tied to how it's going to work in the end, with a bit of randomization. And so I will rather move a bit on. other questions? This is not easy. Please go and ask. There is enough time, I think. So who knows numerical integration from school and who knows it from computer science here in UCL? So the first thing, who did this in school with this trapezoidal rules? Yeah, I think this is something that many people do. Good. Okay, and ever used this in computer science for doing anything, like in image processing? You say yes? There's one person? Yeah? Okay, cool. What rule? Because there are many rules like trapezoidal and horizontal. Do you remember them? I just explained one of them where you just say it's a box, but there's also another variant where you use the gradient and so on. Trapezoidal, I think it's the one where you put like, it's almost the same thing, but if you have your function, when you take a value, you could either say it's constant and you get the area of the box, but there's another trick. If you know the derivative, you could do this, and you assume this derivative just continues, and then you can compute the area of this entire thing with it's a box with like a tilted top, yeah? But for this, you have to know the derivative, and I think I don't know the derivative of this function, and yeah. But maybe there's chances in it, so people always felt like if I have a way to do something with derivatives, maybe I can make this already better. So taking the derivative of the entire thing could be something interesting for research, but nobody could really do it well at that point, and yeah. Okay, so I'm not totally want to smash this, but I think you all agree that if this is 10-dimensional, there are just so many cubes that this is not feasible anymore. But lucky enough, there is some very simple alternative, and you will be disappointed that it's so simple, and I make such a fuss about it, but I want you to understand why people do it. So the easy fix for the entire thing is, I have taken 16 samples in a regular arrangement. So a very simple way of overcoming this entire thing is just to make these guys random. Yeah? So don't put them in a regular layout, which is not going to scale well to high dimensions, but just take them random. So this is uniformly random, just taking points. They might even fall on the same position. They might be empty or whatnot. Anything can happen. But I think you agree if you draw any of them, the probability that they end up somewhere is the same. So why not? Let's try this. And if you do it here, you would have 11 guys that are falling onto white, if I counted correctly. You would have 3 that fall into the dark area, and you would have 2 that fall into the bright area. If you do the math, you get something. Yeah, luckily it's a bit worse. So then the estimator of the integral with randomization, it would say 0.8125. That's this one divided by this one, and that is also not totally different from the 0.85. It's in the right ballpark. It's a bit worse. This is also what you should expect. These randomized things, they will be worse than the cubature things. Yeah? So some people say you have to do it random and then it will be good. It's not. The randomness is just something you have to do to overcome this cause of dimensionality. If you run any cubature thing, it will usually be better. So it will be closer to the 0.85 than this one. This is usually doing worse. Yeah? I can roll the dice a second time, and I might get a different solution. So now it's 3 that fell on this one, it's 3 that fell on this one. If you do the math, this will give you a different value. And now I got a bit closer, but it was just because I'm lucky. It might also happen that I really get the value, I don't know, by just putting, 13, like 0.85 of them, putting them on white, and the rest, I don't know, on black if I have it. Yeah? And then I get the true solution. So nothing prevents you from this thing really in one go estimating the absolutely true value that even the numerical integration would not give you. But it's just random, and you have to be lucky that this happens, and that's maybe not like, doesn't sound like a good strategy in general, but it's likely the only thing that you can do realistically for the conditions that you're in. In this example, it's not obvious what it's going to give you. It's just introduced an amount of randomness, and you can be better, and you might be worse, but on average, I think you're slightly worse. But why is this helping? This is helping because if you go back to your ray trees, what you're going to do now, if you have depth d and you have n samples, this is not going to be exponential anymore, but it just multiplies up. So if you want to have your 1,000 rays every time and you just want depth 3, what you would do is instead of every position here, exhaustively looking into all the other directions, and then for all of these at every point doing the same thing again, you would just go down a random path. So it might happen that you do not look at this one, but in the limit you would, so that is maybe fine, and you just take any random path in here, and you make effort in the order of 3,000, and you have evaluated the entire, so to say, span of how your rendering equation is defined, and everything has its chance of contributing to the value of the integral. It's randomized, yes, it's not the correct solution, but the other thing is also not the correct solution, because if things are too small for your little bins and so on, this is just a bit worse. We will not go into the details of how much worse, so there is this O notation of how well an estimator is approximating a true value of a certain integral or differential equation or expected values. We will not go into this. I just mentioned it's slightly worse, but in practice, it's the only thing that you can do unless you want like 1 billion instead of the 3K that this would amount to. Yeah. So another way of seeing this is, again, if this one would be this point over here that I've been discussing, for getting the value over here, you look at other points in your scene, but not at all of them, but just in one random direction. And at that position, you again take just one other random direction. So what you're doing, you basically take points and you link points to points instead of linking full solutions to full other solutions. And you always just look at one aspect of this very complicated integral. All the domains, you just take a random point, you're evaluating this, and it would still work without having this cost of dimensionality. So a bit more formal. All that has changed is in your summation where you take your samples, you just, instead of trying to do this regularly and subdividing this into cubes, which is going to explode high dimensionally, you just place many samples, it should say random integral function, place as many random samples, so I'm sorry, it should say many random samples, n onto the domain, and you just evaluate f again, and you're averaging the entire thing. And just by doing by introducing the randomness into the entire thing, you're overcoming this problem. So a bit more explicit, and then you can tell me what you think about it, or if you get the idea. So it's still a very simple method. It's not even so different from the cubature. And to get Lx omega out, yeah, so you would n times now, just instead of going over all the directions, you take a random direction for a random incoming direction, that's the 0th one, and you do this at x, so you're here and you take a random direction. You might end up somewhere else, it's the y that I put there, and you then just take another random direction and you're always evaluating. This you must not ignore, so every time when you take the direction, you have to put the two directions in, evaluate BRDF, evaluate the cosine term, and of course this involves ray tracing, so you're basically now sending random rays instead of sending rays that follow certain laws, either regularly or just the reflection ray from good old ray tracing. You just send random rays now and you see what you get. Yeah? And you evaluate the triple product and you're done. And in the end you divide by n. Yeah? So it's averaging the entire thing. Okay, so question on this one. Yeah.
Are we interested in progressive refinement? Sort of, do I want, I could use this to sort of, I could start with a low number of samples and increase the accuracy for the solution. What would that look like? It would be sort of a, as far as the image is concerned, because we might be interested in not waiting until convergence.
Yes. That's one of the, who said complicated?
I'm sorry?
Somebody said complicated? No? No, okay. It's not complicated and it's a very good idea. Yeah. So this is something which is one of the main selling points of this entire thing, because when you take n to be 1, you will get a rather coarse approximation of the thing. When I shoot at this 0.85 thing, on average even, when I shoot often enough, I get the value 0.85. Yeah, of course I have to run many times, so that's a bit unfair and so on. But it will, in some sense, it will already be a good approximation of the true thing. Hold it. Because my battery is starting to turn off. Well, let's see. Yeah, good. In some sense, you will already get a very good estimate even with a single sample. If you just repeat it often enough, that's almost the same as saying I do it n times. And then you can always immediately show the result. Whereas if you do this and you have a certain budget, for example, of doing, I don't know, you do depth only 10 because it's very limited what you can do because you don't have so many rays. So you send all of them here. So you spend 10 of finding out that it's 0 all the time. And then for this sample, you will have lots of zeros and it will not show anything. Whereas if you do it in a randomized fashion for lots of samples, let's imagine like 10 out of them, they will hit this. So every 10 pixel will be bright, and then if you squint your eyes, this is also a form of averaging. This is what people very often do. You just maybe blur the image. There are lots of tricks there. You can write lots of papers about this. This is it's good fun. So if you just look at the entire result, this will already tend much closer to be correct, and it will not have any structured artifacts because everything is randomized. If you roll your dice often enough, and just properly randomized in the limit, this is going to look good. So in particular, what people do, if you want to ray trace, I hope this will work because this morning I got this done, what you just asked for in the WebGL thing. So you just move around. You will see it progressively refining. You will start to see the light, and it will first be very noisy because it's randomized, and then it will converge to something that looks close to the result. And if you let it run overnight and you come the next morning, it will be the ground truth thing in the limits of your machine precision, because after 100,000 samples or something, it will just be right. Yeah. Okay. And this is also, because I said I don't want to bash this numerical integration. Some people say you only have to do it in random and so forth. So it has its use, but also this has its use. So whenever in something else, which is not the rendering equation, you come around a problem like this one, where your dimensionality is too high, using Monte Carlo to also solve this is a good idea. Yeah? It can solve many, many other things. So if you know how this randomization here relates to the integral equation system, there are lots of other integral problems where you can run Monte Carlo and that you can also solve. I'm not expert on these, I only know about this, but say fluid mechanics, deformations, antenna, and so on, all of things which have to do with physics and where an integral appears. This is maybe a good, or sound propagation. Yeah, you will have diffraction there, but you can model it as integral equations, and then you can solve them using Monte Carlo. Yeah. Yeah.
Picking up on what you just said, so we'll always end up with residual noise in
Yes.
the image.
Yes.
So basically, we're going to have to run some kind of denoising always.
Yes, not always. You can.
Okay.
We can. When I have time, I will discuss this a bit because I'm a big fan of doing this, and it took like, I don't know, until recently, like 10 years ago, people started realizing this and they hopped on it, and everybody is doing this now, and it's a good idea to do it. But before, nobody ever did it. So I can discuss this a bit, what you can do there. And you can try at home. You will have this path tracer at your disposal. Maybe put it in Photoshop, blur it a bit, and see what you get. Okay, I would continue a bit. Or no, there's 12. Let's have a short break because I think this is a good point of taking a break. 5 minutes. Can somebody help me trying to get internet here? Because I want to demo what I have in WebGL. Internet? Somebody?
Do you not have a login?
I don't fully know. Just somebody shows me, please. Coursework?
Yes,
Oh, no. Yeah, first internet, then maybe coursework after the game. I have this, but I think this is not
Oh,
going to work.
if you go into Eduround. That one. And then
Because I have the framework, but I need to reload.
yeah,
So which
your
one?
account name is
Yeah.
the number you log in with, the string you log in with Moodle, at UCL AC.UK. And then you just put your Moodle password in.
Moodle password, this is my general password.
Yeah, this one.
You'll see each wanted to jump over.
Have any idea about this? There seems to be some Mac dialogue again. Why
It
again?
asks you to accept because the certificate is a bit weird.
Yeah.
So you have to accept it. So you have to log in.
With my Mac thing, oh, what is it? Oh, so good. Because then I can demo much nicer. Cool. So, coursework, yeah, maybe. But also it's better afterwards because it's also full. If I just show me, I will think about it and then I will see. Because it's a longer thing.
Okay, so basically, I have the HTTP buffer.
Yeah.
Well, I have to find
Yes,
the
yeah,
device
that's cool.
segment.
You're debugging it with this one, yeah, that's so cool.
So this is just the device segment.
What I've noticed is if I read from this
It only works if I
what I read.
if I completely ignore depth sum.
But how do you get that?
I've yet to like
So
in my life I might have finished 2 books.
I get depth sum here and I do it with color. But the color now looks, if I divide it by depth
Why
sum,
do you divide it by depth?
You must have read
this was there already.
like the high school
This was part of the boilerplate
bad
credit.
things like that. I read Sparkle, like summary of the book, and I get by. You can't read Jefferson's I mean, I'm not really exaggerating, but like still, like I try to avoid.
Yes,
Yes, so it's part of it. So if this one, when I
Now I'm
divide it by
getting
the
into it
depth
again,
sum,
like because
the colors become really
what I've
saturated,
noticed
like
in high
really,
school
really
it goes
strong.
worse the way you
and weird.
but now like I
Oh,
on
yeah.
top of saying,
If I divide this by depth sum, this just becomes white. It's like I have to do
No, everything should be weight sum. What do you get when you do weight sum for everything?
I didn't try that. We're only dividing color sum by weight sum now.
So you should always just divide by weight sum.
By the weight sum.
yeah, for sure.
Okay. So
So we have these mechanics that allow you to maybe see already something if you didn't have a complete solution, and that is maybe here not configured correctly.
Okay.
So why is it gray? Because you're outputting depth as color, or why is it gray? Because
Oh, this one is because I'm just using the Z as the color.
yeah, okay, then I cannot tell you if it works. But this is what you should try then.
Okay, this. Okay.
Let's come to me after the thing. Yes, again.
Hi. We have a question.
You're all talking.
So the thing is, the things we're getting, like
But you told it, you have seen this rotation thing? Yeah. So, okay, you didn't. So this is something that already told you that everything is shifted by one?
No, we asked them on this.
I mean, I don't think I'll
CD, but they haven't done it.
So I already have the draft
Okay.
of the announcement.
so the question was, this figure is not
It's not correct.
Okay.
No, this is not updated, so we're going to do it for color. It's so many. I can't really tell if you shift them now, you get this. Yes, it's really about having animated. Others is always what the TA method is. It's really this plus one. I just didn't realize that you have to get the opposite. I took the wrong.
You have to work.
I have the one who usually reads like the team first one, and I can send it to the other guys after that, but they didn't respond, and we will put it on our way. And because I show you some of these stuff, it has some bugs.
Like you find it. Yeah, you find it they're inside the clip you're outside.
Okay, so both are, one is outside, one is inside. You just check for
Yeah, okay. It's the same one that the other guy has. I will say it in public again. It's the same problem that you have. I will say it in public again.
Is it
No,
compulsory to ask, is it compulsory to use the functions, the structures that have been given, like, no?
Unless you have a good reason, yes. Unless you have a good reason, yes, I would say. Yeah. If you have a good reason not to use it, then maybe. Yeah.
In Sutherland clipping, where, it is assumed that we should use the get crossing type function, we can also manage with just finding that whether this a particular vertex is on which side of edge. So on the edge function, using the edge function, we can do instead of get
You will
crossing.
show me later. Yes, maybe. Yeah. There are different ways of doing this. This I know. Yes. Yeah. Good. Go away. Okay. 1, 2. Let's go on. Okay. So first thing, people asked me about the coursework, so I will just briefly repeat what I said to the others. No, you're all listening. So there is another issue that we have with our code, and there's another thing which is not perfect. This is path tracing. This is not. I will not show it. There's one thing which is just a bug. There are bugs that the TAs put, and there's one bug that I put, and this is the one that you're all facing now, and I just have to explain it. There is this barycentric interpolation, and in the way that the vertices are defined in the exercise, if you do it correctly, you will not get the output that is in the PDF. You will only get the output which is in the PDF if you do the same bug that I made. So the bug is really what I did. You have to, basically you are the point and you have to look at the two opposite points, which are +1 and +2, and all of you seem to do this correctly, and just me, I did it wrong. I did +0 and +1, which is the same as if I computed for the next point, yeah, because everything is then shifted by 1. So you get a triangle. If it's red, green, blue, you will get a triangle that is blue, green, red, just everything shifted by 1, yeah. So this is an easy fix. Of course, we will accept lots of solutions if you do something approximately right. Most of you come to me with solutions which are already so good, I will fully mark them. I just want to see that you do kind of the right thing. So this is, and we also show you those images to give you an idea of what this looks like. And this is not like mandatory that everything there should be right. I'm already a bit shy to put those images. It would be very easy for me to not put images and then after the fact just find my bugs and then just silently give you all lots of good marks. I will not do. I give you I show you those images, but they are a suggestion. So let's do this handshake. Don't take them word by word. You can't do this. I mean, I'm redoing the entire course. I'm doing this framework and I'm doing the exercises, and there will be bugs. This is something that is in software. Next year, if I just give the same exercise without bugs to other students, yeah, then there will be no bugs. But this is something that just happens here, and it will happen. And with this one, it happened in this case. So again, these are shifted by 1. If your colors are off by 1, this would be fine. Whatever you submit, if there are colors on the edges, which are the colors from the vertices, even if they're shifted, we will accept this. You can fix it. You can reproduce our error. Rather don't put our error. Put the right code, and we, of course, will give you lots of points for that. There's another subtle thing that I also asked the TA. I will also put all of this on Moodle. We also have the text for this. It's not yet there. There's another thing which is not super correct. I'm asking for perspectively correct interpolation. You can do this in 2 ways. And the way the coursework is asking, it suggests doing this in the clipping. You don't have to do this. If you can get away by doing this in the interpolation and doing perspectively correct interpolation by using the unclipped triangle instead of making new perspectively correct color vertices, color values at the clipped vertices, that's one solution. That's what the PDF is suggesting what you should do. But that can be more difficult to what the code already almost does. It doesn't even compute them properly, but just in the interpolation, use the unclipped triangle, and you perspectively correct interpolate these. But do it perspectively correct. This I want to see that the division by the z and so on is done in the right order. If you do this, I don't care if you put it in clipping or you put it in the interpolation. It's 10 points. If you do it here or if you do it here, I don't mind. So it's not like that if you don't do it in the clipping, you don't get those 10 points. No, wherever you do it, I think the second one is slightly easier. You will get your 10 points for this one. Yeah. And always ask also the TAs. Of course, you can come to me, but they usually know, and we acknowledge this is a bug. But you're almost through, so I don't think there will be too many other bugs more. Okay, and yeah, thanks for reporting them. So here I'm showing what it would look like if you run your path tracer. This is not yet very pretty, so what this would do, it's the minimal thing. You just send a random ray through every pixel, and you terminate very eagerly, so you don't go down at all. You just terminate after 1. So we'll get some spectacularly ugly image. Not even the sphere is correct anymore. It's even jaggy on the boundaries. Whoa, how can it be? Yeah, and this is also not super interesting scene, but it already is a bit more because now you have already a light source, so you have a spherical light source. This object now doesn't have, there are no point lights anymore, the class point light or anything, it's gone. I don't have it in my code, but what I have in the material, I have extended them by a field called emission, so every material can now emit, and I think you can guess this is a sphere that is emitting light, and you can already do much more realistic things with that. And then there are little pieces in the code. So there's something called max path length, which will tell you if you take a random path, how quickly you will stop. Yeah? How often will you roll the dice? So it was 1, so you roll it once, you go through 1 pixel, and then you don't keep going. And if you do this twice, I have to reload this here because we don't have a way to reset the image. It's a bit dysfunctional, but it will be fixed before we get to it. Yeah. So this is after 2 bounces, and this is already a bit more interesting. You get a bit more of an idea what happened. So there was a ray being sent everywhere, and then very sparsely only you get bright points. It sounds a bit disappointing. At least you get, because here you hit the emissive object, and it will be then some constant plus very unlikely other stuff, which might be, I don't know, there's no other emissive object, so +0. But in other places, there is blackness because there is no emission, and you take another random hop, and then there is some slight chance, I think you can guess the scene, there is something here, maybe some of you see the red dots here. So in some occasions, you were lucky, and after rolling the dice, you were choosing a direction such that then you hit something emissive. So you had 0 plus something else in some of the cases. Yeah? And if you just do this often enough, let me see if I can do this here. Press save. No, I would need to reload. I will just get a different image. It's a bit difficult to say now, yeah, but this is different. Nobody remembered what the pixels were, but this is different, yeah. And if I keep doing this, I will get even more indirect things, but this is not really, this will really be hard to discern. So what people are doing is rather this one that you asked here. So I will take 2 rolls of a dice, and I will average them. That's the rules of the game. You have n samples, and you're averaging them. You would get something like this. Oh, it's not so much better. I think maybe that you don't see enough. I will just give it a bit more. Maybe 100. Oh, yeah. Good. And yeah, you already see this is going somewhere, so you start to see what the scene is like. I will not put 10,000, but you see that you have this very bright sphere. It's way beyond anything which is a light source. It's a sphere that just sends light, and it casts something that is a shadow, but it's so much more subtle. Even if it's noisy, you see that it's soft and so on, and it even reflects kind of in it, and you get the gradient. And even if you just look at it, like squinting your eyes, you feel that this is like you almost see how it would really be, what nature would be like, and that I think you feel that this is really solving the right equation. It takes its time, and still it's noisy and everything. And these are all limitations we can discuss, but that this is going in the limit to the right thing that just does everything in some way, I think you see it, yeah? So you let it converge a bit longer. I think I have something wrong with my random number generator in WebGL, so we invited to fix it and so on. So now it goes for 10,000 or whatever I put. And wow, this is cool. This one is not being anti-aliased. You can think a bit about why this is. This is a very advanced thing. You will only understand if you think very long. But this is anti-aliased. So here you see what I described. This fact that I don't shoot only always the same ray to the center of the pixel, but I have a rendering equation which includes the integration over the domain of the pixel. So instead of always sending the same ray as you did before, I take a random subpixel location and I average all of them. So this pixel, see how soft this gets. It never is really either the background or the foreground, but it always is exactly the solution of the integral, which just takes the expected value across the entire pixel. And oh yeah, this is converging really nicely here. I think it got faster because I connected my power. This is something, because at home when I worked on it, it was much, much slower because I had no power. I think this is a Mac thing. Yeah, I think this is an acceptable image at that point even, yeah? I don't know why this is slightly pink here. Is it the projector? Or is it? Yeah? So I will not show you the code fully because you will program something in that direction. I didn't yet fully decide, but I hope you like the image. Is there something that you want me to try? There's one interesting thing to try with this, which is left. Good demo. Any idea? What can I change? There's another parameter I already discussed. I changed to 10,000. What else can I change? Come on. No? I put here the number of dices that I'm rolling. So it's 2, and I put 3. So I terminate them at 2, and I don't keep going. And it's not obvious if for this scene this is going to make a huge difference. And I think it does. So we have to wait a bit. There's something wrong with the random number generator because in the beginning it's so bad, and then all of a sudden, like around now, it gets better. Usually it's the other way around. It's converging slower and slower. So I mentioned to you there are different rates of convergence of like numerical integration, randomized, and so on. And this has, I don't know, O of, I think, square root. So if you want to make the image like the arrow half as large, you have to do quadratically more pixels. But for numerical integration, it's also not that much better for cubature. Yeah? So no free lunch. It's not like something that gets better and better, quicker and quicker or something. It's not like that. It gets harder and harder. So who sees the difference between the 3 random throws and the 2 ones?
There is a reflection on this one sphere.
Yes. is this stuff here. It's rather small and it's noisy because it's difficult to resolve because the integrand has a high variation. Don't say variance. Variance is the noise variant here. So this stuff is what you got. And if I would tone map the entire image a bit different, so I would translate this onto the Beamer values a bit differently, you will start to see those values. And if I put 4, it will get slower, but maybe it won't change much visually. Yeah. But it has very simple and intuitive parameters, I would say. So nothing like, I don't know, in OpenGL where you say number of vertices and here and shader there. It's really just a very mathematical thing all of a sudden. Yeah, so now we'll go to details. And last chance to ask in general how this Monte Carlo is going to work, how you would implement it. Randomness is the thing. Random race averaged in an organized fashion. Yeah. No questions? Good. So we already discussed a bit when to stop. There are multiple popular options after a fixed depth, what you just have been seeing. When the contribution falls below a threshold, that's what I showed here. I even discussed the more advanced variant where you do not just go to a threshold, but instead of making the decision, you roll another secret dice, and only if this dice is below the threshold, you terminate. Because only this would allow you to be unbiased, so that when you run it for infinity, you really get the true solution. Yeah? And everything else is called biased, and that changes something. There's something that I will not do in this course because I advertise so much that it's easy, but this is something that almost every Monte Carlo path tracer does. That's called next event estimation. So what I explained to you is to just take random race and just go. What they do rather instead, if you have point lights, but you won't have point lights because it doesn't fit the theory here, so it's not really good. But if you have ever in reality, you will come across something called next event estimation, and instead of picking random race, so when you here maybe got to this point, you will also directly link to the light. Because you know where the light is, you can basically cheat and ask, okay, what would be the random number I would need to take to go to that light source, and then you can be sure that you hit the light source. Because with this, you saw with a single sample, most of the things were black. Why is this? Because it took a random value, and if you're somewhere in the scene and you have a light source over there, there are lots of options how you can go without hitting the light, so it will be very unlikely. So you can improve your chances by biasing a bit more to go there. But there's another piece of math which is too hard for me to do to get this correct, so we will not do this, and you will not implement this, but you will come across this in reality if you ever operate a renderer. They usually have next event estimation, yeah? Because connecting to anything non-light is useless. Connection means also indirect connections, but anything will be useless. There's another thing, how to pick random directions, because I said you're on the hemisphere and you roll your dice. That would amount to taking a random direction on the sphere or on the hemisphere. So it's tempting to do something like normalize and then a function called frand, which I usually have. It's the same like rand, which you should know from C++, just that it doesn't return between 0 and 2 to the power of 15, but it returns floating point numbers from 0 to 1. And it would be tempting to do something like that. So that's wrong anyway, because it will only give you the positive numbers, but you multiply by 2 and you subtract 1. You just scale the stuff appropriately. Even this is not going to be correct, but that's not super intuitive. If you were to run something like that, this is from Mathematica webpage, you will see that you will get a distribution of points on the scene which looks like that. So you have a clumping here around the pole. If you just take random, like 3 independent random values and you normalize this, you can see that you have a higher likelihood for certain directions than you have for others, in particular along the axis, so here it would cluster. Whereas if you do it correctly, which I will not explain in full, it's in the code already, you can get really random 3D directions. So random 3D directions is not vectors with 3 random elements. You need to do a bit more to get this right. Yeah? And this would bias the result, so then you have a light source and it's shining, and then inside the sphere it would give you an even distribution because everything is equally likely. If you do this, it would bias it, so you would get brightness here and less brightness there, so it will give you an image which also maybe looks cool, but is far from the solution of the rendering equation. Okay. So these are just 2 things that explain you why the code maybe is like this. This is 2 ingredients you will need to have. There's another theoretical thing I would like you to understand, because randomness, when you look to the internet, why people use path tracing, there are other reasons being put forward. And these are only half of the story, but they are still true. So randomness has another reason. So alias is the second reason for having something random. Consider this very simple integrand. It's one-dimensional, and it's like it's white and black just in a step function, just changing all the time. If you take your cubature, so this is the non-random approximate numerical integration, and you regularly put the samples, you can very easily be out of luck in such a regular arrangement, and you're sampling this thing, so you put this in the middle with a single sample, you will get 0. Okay, with a single sample it won't be that good. The true value, of course, is 0.5 or something, because you have to average white and black all the time. You take another random arrangement, so in a regular arrangement, on top of a regular arrangement, there is a chance that they will align, so that the frequencies of the signal and the frequency of your sampling patterns, they are in a certain relation, in particular they get the same, and then you're really out of luck because you hit black twice, and you get black again, which is again very off. If you imagine what this would do for random, I think chances are better that if you choose something random, you also fall on something which is white, and you have a much better idea to getting the right value. And this goes on. So if you really take 1,000 samples and you have a frequency of 1,000 and it's regular, like imagine a fence, for example, that's on a single pixel, yeah? So everything averages in the pixel, and you have a fence with 1,000 bars, and you have this unfortunate sample patterns, it will tell you 0, although there are lots of chances to seeing that this was not 0. Yeah? So the ground true would be 0.5. And this is random, so here I have to put this, of course, now in a certain way, so I try to be a bit fair. So with a single random sample, you might be in the middle, but you might also be in the other one, so it's either white or black with a single sample, but in the limit correct. And if you start to do more, I think it's really fair. You can do the math, I can't, but like in probability, you can, I think, do the math, how likely it is that it will fall n times on something black or n times on something white. I think it's this Bernoulli distribution. It's much more likely that we'll have a few that fall onto black and a few that fall onto white. And with more samples, it's kind of guaranteed that this is going to become small instead of staying white or black as you would get if you choose this random distributions. So two reasons for Monte Carlo, one being aliasing, this effect, that certain repetitive patterns give you wrong values, and the other one is the curse of dimensionality. None of them alone is like a full explanation, I think. Okay, and there's this other effect that you do not really get a value, but what you get in reality, this is now a bit of an abstraction. If the true value of this integral that I wanted to estimate is 0.85, this is not samples, but this is, so to say, the result, and it's distributed around the true value. So now the real true value is maybe 0.85, it's somewhere between 0.9 and 0.8. What you get if you run multiple times, you just saw it in WebGL, you will always get different images, so you get different pixel values. Yeah? And on average, of course, you will get this one with an infinite number of samples, but in practice, you have a distribution of values that you will observe around it for any finite number. And you want the variance to be small. So if you have a good estimator and a good technique, ideally when you run multiple times, you get like images which are not off from the true value, but which are really close to this, and this is called variance. And yeah, so a good estimator has a low variance, and whenever we render, we will get a value close to the true value. What you don't want is bias, that if you run it infinitely often, you get a different value, then something is wrong with your code. Then your random number generator is not right, or you did an error in the math. Yeah? But variance is inevitable. It will always be noisy. It will be noisy between pixels. It will be noisy if you run it multiple times, always a different value. Just in the limit, it's correct. If you run many times, you just do the average on a piece of paper, it converges to the right thing, or you let it run 10,000 iterations, it will converge. Yeah? But still it has variance. It's inevitable whenever you do this. Yeah? And what you would want to do is variance reduction. So yeah, to get this variance down, and there are certain tricks that you can do, and I want to mention them here. I have the slides in a bit funny order I see here. So this slide should maybe be before that, but yeah. So this is just saying again what we've been discussing. If I take n samples, you get an image. You can look at that. That is what you just saw in WebGL, and I hope you liked. And after 2 n samples, you get another image, and you can progressively look at this. And this is very useful for previews. You don't have to wait to the end to see the image, but you always are up to date very easily on what the image is going to converge to. And because you can use your brain to get an idea if this is going to work, or if your object is upside down, you will very quickly see, and you don't have to wait to the end like you render by scanline, and you wait 2 hours, and then 2 hours later you see that your bunny is upside down, and you wait another 2 hours. This would be very unintuitive to handle. Not so this one. It's very, very good usability. And that's called progressiveness. It's another positive aspect of why to use fast tracing. But I mentioned this variance, so this slide should come next. It's variance reduction. And there are 2 things I want you to remember how to get the variance down. So how to slightly change Monte Carlo estimation and add a little extra to get the distribution of images, not sometimes being a bit more than 0.85 and sometimes a bit less, but to get it tight, that how often, no matter of how often you run it, you always almost get to the 0.85. If you had perfect variance reduction, then you always would get the 0.85, but that would be then the same as doing it analytically, and that is usually very hard. But these are independent of the problem to some extent, and they can always be applied to everything. So whenever, for example, if you want to simulate antenna in your next career, all of these do also apply. So if quasi-Monte Carlo is your thing, it also will apply. Important sampling, same thing for antennas. All of these can be applied. Yeah. Okay, so there is and there are two things that you can do. One of them is doing something to the sample pattern. So I said just take your points random. We can improve upon that and still get the right solution. And the other thing, and there are different incarnations of this that we will go through. And the other one is important sampling. This is making sure that you take samples more likely in areas that do have a high contribution to the integrand, because the higher the contribution to the error is as well. And so you rather focus your computation on where it is important. And this is two strategies, and they are orthogonal. So you can have both, and a good renderer will have both of them. So the first one is taking a good sample pattern. This is, again, very intuitive. So we get back to this little structure here, whatever this would be, that you're trying to integrate. So again, we're still looking for the 0.85. Yeah. And OK, now I made my error on those slides. This is, of course, not 0.856. I forgot to change it. I will change it. You will be confused. Yeah, it's like far from 0.85. Instead, it's 1. So I took 16 samples, and nothing prevents me from, when I really take random things, that they will clump. So they look at the same value all the time. So you're, again, computing the same shadow twice. That already sounds wrong. Yeah? And at the same time, this guy is, so to say, missing to do the right thing, to cover maybe, to explore what's going on here. So it doesn't cover that area. And if you're really out of luck, it maybe even doesn't cover this. And then you get a value which is very off from the 0.85. It would be 1 on the end of the spectrum. Nobody knows if this distribution is Gaussian. I always have to review 3 papers a year that say it's Gaussian. It's not. Everybody knows. So it's not Gaussian. It's like a complicated distribution. But it's getting, of course, unlikelier that you get images which are very off from the true value. So because this distribution, if you roll random dice to get like a big area where there is nothing, it's rather unlikely. Yeah? But it can happen. There's no problem. There's a non-zero probability that it will say 1, although it's 0.85. So there are 16 points, 16 of them set wide, you divide, you get 1, and that's very far from 0.85, and that's not so cool. Yeah? So, yeah. What's wrong with the sampling pattern? There are two contradicting goals somehow. What you want is, you don't want it to be too regular, because otherwise you get this course of dimensionality, but you always want to also cover the domain uniformly, not only in the limit. So if I run 1 million of samples, it gets even unlikelier that I will have large areas where no samples are falling. But in particular for a low number of rays, low number of samples, so that's a fast method, yeah, it would start to have a non-negligible probability that there are some areas that it doesn't cover. So what you want to have at the same time, it should be somehow random, but also have no holes, yeah, and that's a good sampling pattern. Yeah. So I will give you a few examples of how to do this. So one of them is a bit going back to the future. So you saw how cubature doesn't work, but there is a method called jittering, which is putting back a bit of the cubature into the randomized Monte Carlo again to make sure that things work better. It suffers again from the course of dimensionality. So if you want to simulate many, many bounces, this is not going to work very well. But if you have only one bounce where this d, this exponent, is more like 1, then it's going to work still very well. And in some cases, this is applicable. For example, you can imagine a ray tracer that renders with 50 samples the direct light and then 50 samples the indirect stuff. And if the 50 samples in the beginning, you have to choose those samples, then maybe use this method. It suffers from the course of dimensionality, but it's even better than cubature. It would not scale to something high dimensional. So maybe just split your image, and for this method, you could use this. Yeah. And yeah, it's applicable if dimensionality is low. So if you do area light sampling, if you have your ray tracer, and it really does next event estimation, an area light, it has the degree of freedom of where on the light source you're sampling. And there, very often, they use this pattern. Let me show this pattern to you. This was regular. This doesn't work for the reasons I have explained. Jittering is no more than that you take this pattern, and instead of drawing a random sample in the entire domain, you just take a random sample into this little subdomain. But you just make sure that into each of them, you put a sample. And I think it's somewhat easy to see that this does not scale to high dimensions, because if you already say, I put one sample into all of the bins, and a hypercube with 7 dimensions with 10 on the side is already 10 to the power of 7, you cannot even start. Before you randomly move them, you're already dead because it's so many samples that you cannot do it in practice. So that's why jittering doesn't scale to very high dimensions. But at least there are no holes anymore. So there's no way that you will miss this guy, you know, because wherever you move this in here, it will never be in a location where you don't explore it. So you have much better variance reduction. So if you look at all the results, the distribution around the 0.85, if you apply this, it will be much tighter, and most of the time it's much closer to 0.85 than it would be if you just throw random things. This one is clear. Should be clear how to do it. That's trivial. This is really a little programming exercise. But why it doesn't scale, this will only be understood when you understood why the cubature is not what you're going to do and the numerical integration with little cubes, but you do randomization. Okay, so there's another thing in this pattern which is not super good and that could improve. And I intentionally did it. So who spots it? Like there is something which is not so good. Nothing? I'm just curious. It's like how humans see patterns. Any idea? Come on, say something. No? Yeah? Yes. Yes, yeah. This looks a bit intentional, no? These four here. Yes, that's it. Very good. Cool. So why would it be maybe bad? So first it's good to see it, yeah, that I put something intentional, but how could it be bad? If they were somewhere else, for example, would it then be maybe bad? So more like here or so, yeah. So it could happen like the closer they are, the likelier is that these areas, they get large and the more space is there for something going under the radar and not being captured. So if they were, for example, here, I can still manage with multi-jittering to all put them here, and nothing is won because this entire large area here would be black, and also here they just do not cover well. So you maybe wanted to even go beyond, and you want this. So you want them to all go into one cell, but at the same time they also should kind of keep their distance. So whenever one cell puts a guy here, you have to make sure that in the next cell you don't put it exactly in such a position that then they start to become very small, because then you have a large area where things could fit in that do not really work well. And this is called multi-jittering. So there's this little piece of software that just says, okay, divide by number and then plus 1 divided by random. That will just put these. I think you can all imagine how this works. It's much more complicated to get this right, but it's again a 3-line thing that you can find on the internet, and it's called multi-jittered, and will make sure that these configurations are not happening. And that's, of course, that's a real workhorse. So many vendors really use this pattern for many things, because if it's low dimensional, this is what you're going to use. So if you go to the movies and you see an area shadow, it was this guy usually. Okay, but it doesn't scale to high dimensionality because of those number of cubes. And then we will go for something else, which is called Halton or other more low discrepancy patterns. That's what it's called. And they are somewhat uniform and they're without structure, but they still will scale to high dimensions. So this is then the workhorse for everything high dimensional. So what we're after now is just a different way to, on the unit hypercube, to come up with a sample pattern that is random in some way, but at the same time doesn't have the holes. Yeah? And to understand this, you have to learn something that I hope you didn't see in school. It's the radical inverse in base n. So this is, for example, the radical inverse in base 2. And it's no more than saying I take 1/2, yeah, because this is 1 divided by 2. That's the first 2 to the power of 1. And you go to 2 to the power of 2, which is the 4th. And you basically... The radical inverse in base n is a sequence. So that's the first element of that sequence. The next element of the sequence is 2 to the power of 2, and then everything in it which is not already in that sequence. So that 0 we don't have for other reasons, but 1/4, this would be part of the sequence. 2/4 would not, because 1/2 already is. 3/4 again is, because there's nothing and you keep going. The same thing then for 1/8. So 0, again, we ignore. 1/8 is not there. 2/8 is already there. 3/8 not. 4/8, I think you got the idea. This is the radical inverse in base n. And I think you can write a little piece of code to do this. It will take forever because it's not so easy in practice to write it. But again, it's something that you can find on the internet. Let's just assume we know this is a radical inverse in base n. And you can always then do this also for other bases. So I did this in PowerPoint. Maybe you can spot an error, but I think it's the same, 1/3 and 2/3. So on the first level, you already have 3 of them. Then you have the 6ths, which are not already in the 3rd. You have the 9th, which are not already in the 6ths, and so forth. And this again gives you a set, of course, with many more points. And the sample pattern, which is called Halton, it takes the radical inverse in the basis pi 0 or pi 1. So pi is enumerating all the prime numbers. It's a function, when I give you 5, it's the 5th prime number. So if you want the Halton pattern, which is 2-dimensional, you take the first 2 prime numbers, which are 2 and 3. This is the pattern for 2. I omitted the numbers. This is the pattern for 3. If you want this to be 10-dimensional, you take the first 10 prime numbers, which I don't know, but you will find a way to find out. And then you pair them in a way as I'm showing here. So the first element would be the first element in the first basis for the x-coordinate. And for the y-coordinate, you take the first in this sequence, which is the 3-based pi 1, 3 basis radical inverse, and that gives you the y-coordinate. And then you repeat it. You go for the x-coordinate, you get this one, and you already see even the first 3 samples, because it was very systematic, but at the same time, they kind of cover the unit sphere well, the unit domain well. So it's not like they're all here in the corner or something like that. They kind of cover this entire thing well. And if you program this really to the end, you will get something like this. So this is from Wikipedia. This is maybe what you would get for maybe 10 samples in red if you draw random ones. You see there are large holes and others where it's clumping. But if you look at the red ones and you see them in Halton, they're much more nicely distributed. If you look at the blue ones, I think they are a bit rarer than the green ones. So that's for, again, a lower number of samples. And then you have the green ones, which are very dense. But even if you forget about the colors, I think you agree that this one has lots of holes, yeah, where things can go under the radar, shadows lost, reflections missing, lots of things go on in your integrand and you don't see them. And that's Halton, and it makes sure that whenever you take a random decision, it's likely that other random decisions will be different and you don't look at the same thing again. Yeah? So if I want to get an idea how you like the course, I will not take the same person and ask you 10 times, but I will ask different people to get more of an opinion. That's basically the idea behind the entire thing, to get like a more informed sample of what's going on. It's not very hard to program. So you really have like 2 one-liners. One gives you the x-coordinate, one gives you the y-coordinate, and you replace your random number generator by this magic piece of code. And it's called the Halton sequence, and yeah, it gives you immediately this pattern. Questions on this? No, good. So this is just one point in some other family, which is called the quasi-Monte Carlo sampling. So it's called Monte Carlo, I forgot to say. So it's called Monte Carlo because in Monte Carlo there's a lot of gambling that involves a lot of randomness. And statistics was invented because of randomness, so that's the relation. But it's called then quasi-Monte Carlo because it has similar properties. But all of a sudden it got regular, so there's no randomness in it anymore. If you run it 2 times, you get the same Halton pattern. There are no 2 Halton patterns. It's just that you again have something that doesn't suffer from the course of dimensionality, covers your entire domain, scales to high dimensions, and then immediately it still works. It doesn't need randomness. This is just a means of getting this. Yeah? So all of these methods are called quasi-Monte Carlo. Let me say again, this also works for antenna maybe. Yeah? So all of this is useful for not just rendering. So again, you build the radical inverse in this co-prime basis. Pi enumerates you the prime numbers. So if it's 10D, there are of course 10 prime numbers, so you can do that. And you build the tuples in the order that they occur in the sequence, and you use this for ray tracing. The x and y, which is the first 2 angles, you just use Halton. There's another sequence which is called Hammersley, and it takes just as the first dimension the regular subdivision, and as the other dimension it takes the pi. This is even more used. And because now for every pixel, the pattern is the same, there's another little trick, which is called randomized quasi-Monte Carlo method. This long, very long abbreviation. And it just randomizes this non-randomized thing again and just takes all the patterns and shifts them in a random way. Because I think you can imagine, if I take this and I just shift this toroidally so that when I go out here, this comes in, this is again a different pattern. But it still has the good properties, and then you have like infinitely many Halton patterns that are all good for themselves, but they are not the same, and that makes the pixels look different. Yeah, and then because it might still be that maybe you have a very small light source, and this can still fly below the radar. But if you randomly shift this, the probability that it will not be caught in some random shifted permutation of this thing, it cannot occur, and that's why people use this called Cranley-Patterson rotation that is usually used. So that's no more than just calling your Halton and then adding a little random shift to it to make sure that then it also covers the last remaining details. Okay. And you can go forever. So this, you can go down, but this is basically where I take a cut of how well crafted this can be, and we just look into a few other aspects which are interesting. There's another pattern which I think for you it's interesting to know. For me, it's what was quite fascinating. So this is blue noise or Poisson disk patterns. They have also applications in many other occasions, even in nature they occur. And this is a pattern where the minimal distance between two samples or 2 points is maximal. Yeah, so I will just show you an example. This is such an arrangement. I think it looks already beautiful on its own. I don't know, but this is basically the minimal circle you can make around all of the objects before you hit something else. And a pattern that looks nicely distributed is a pattern where these, for all the points, like the minimum, is rather large. So if you have 2 points which are very close, you cannot make the radius large, and then the minimum over the entire domain is already something very small, and that would not be a good pattern. But you can set up lots of very complicated equation systems. You can write a PhD about this, yeah, that people did with me, that try to find out how to get a global arrangement of points that no any other gets close to this guy, because then the radius would get small, and then the minimal overall radius would be bad. And that's a very good coverage. You see this. It's random. It's not regular, so it doesn't suffer the aliasing. Doing this in high dimensions, okay, that's another question, but at the same time, it really covers well, and you have a very low chance that something will fly below the radar, and it's not regular, whatever you look at it. Like locally, it looks a bit regular, but globally, no pattern at all. And this is a very good pattern, and nature realized that too. So if you would look at your retina, which also has kind of samples of how to get the world in to your brain, it did the same. It's not perfectly Poisson disk, but the tendency is clearly there. When you put them, they tend not to be close to each other. It's quantized because there are cells and so forth, and nature cannot do it perfectly. But on all the retinas of highly developed things, so things with a high visual, like a large visual cortex, all of them, they have Poisson disk sampling on your retina. And if it's good for your retina over like millions of years, it's maybe also good for your ray tracer. Yeah. So remember this, and I think it's really educational and cool. And there are many other things. For example, if you want to put like humans in a plane, they will also try to arrange like this because, yeah, they will try to keep certain distances. So that's a very universal pattern, and it can also be good for integration. Okay, so much on the patterns. All that I want you to remember is you can do random, but random is just something that has certain properties that you can get even better by using other patterns, as I have showed, just like Halton, for example, you should remember. And the other thing that you could do to improve or to reduce the variance of your estimator is to put more samples where the integrand is high, and because here the influence of the error would be largest. So this is a rather dark value, and this is very bright. And if you don't get this right, the influence will be much larger than here. This is black, so at worst, what can do, if this is black or not, that doesn't make such a huge difference. But if this is white or not, it's just 3 times or 4 times larger, and then you want to count these correctly. So whenever you have a chance of putting the samples where you know the value of your function would be high, you should do it. However, this is pretty complicated, so you try to place the samples non-uniformly, and this would introduce a little bit of bias. But fortunately, this random that you just saw is just a special case of a more general estimator of formulations that we will see next. Yeah. So what we did before is when you take a random sample, we said this is uniformly. If it is Halton or Hammersley or whatever you take, like the probability that something falls somewhere is uniform. So the probability of taking this point is 1 over the measure of your domain. For example, 1 if it's the unit quad. So it's just constant. Yeah. But the good thing is in Monte Carlo, any other p will also work. So if you take like more samples on the right half than you take on the left half, there is a slight modification in Monte Carlo, or a more general notation that you can choose, which then allows you to just take more samples here and less samples on the other side. And this is then called Monte Carlo sampling with Monte Carlo with importance sampling. And it just reads, if you want to get the integral, you know the story, you take the sum, and all that you do differently now is instead that you divide by n. This is just, n is just a way of expressing a uniform probability distribution. So what you can also do, you divide by the probability of taking that sample. And if the probability is twice as high, you just count the sample half as much. And if you have a less likely sample, you count it more. Yeah? So if something is half as likely, you will just count it twice. So again, you can read the text. All that changes is now you take the samples according to a probability distribution. And if you do this, you have to divide by the value of this probability distribution so to say, counteract the bias. If you don't do this, you would just put lots of samples here, then it would give more weight, so to say, to the result that you have here. But that, of course, you don't want to do because then you get a different value. It's just that you want to find out more in detail what the real value is. Yeah? So let me give you an example of what P can be, yeah? Because this sounds like something that you can easily write in slides, like just take the samples proportional to the integrand, but you don't know the integrand. The integrand involves things that you know, the BRDF, the geometric factor, but it also involves the incoming light, for which, again, you have to solve other equation systems, and of course, you can't do this. I just explained this. It's like very, very recursive. So it's not so easy to sample for the light. If you are somewhere to know where there's light coming, yeah, so to just send more samples in one direction because I know that this is where the light comes from. How can you know? You can do this for the next event estimation I explained. When you know this is a light source and you have a little list in your, I don't know, modeling package, then you can maybe do. But in general conditions, there is no way of finding out, like if you're here, that maybe I should look here because the light bounced because it came from the projector. That's a very complicated relation. So it's very hard to import and sample for the light. But this is just one factor in an entire product, which is defining your integrand. So this is hard, but the other ones you can do. So BRDF, this is not so hard. So for example, if you have a mirror, yeah, everything except the reflection direction will be 0. I already told you this. Yeah? So it would be a very good idea to send lots of rays into the reflection direction instead of sending them where this factor will be 0 all the time anyway. So all that you need to do is maybe make it 100% more likely to go in the mirror direction. And when you find something, you just divide it by 100. And the rest, yeah, you just send only every 100th ray. And you then have to pump it up by factor 100. And this will even out. And you get, yeah. You're not counting as many zeros as you would do if you just go into the other direction. And there is this other little friendly term, which is not so complicated. Remember, it was just the Lambertian term that just says if you have a surface and you have the normal, it depends on what direction things come from. When it comes from the top, like when it comes from the sun comes from the side on the equator, it's more light, and from the top it's less. And this is very easy to do analytically. So if you choose a random sample, don't do this in a random direction, but take the normal at the position where you're at. And the first thing to do, which I don't do in my ray tracer now, is to go into a direction into the upper hemisphere where this dot product between the normal and the direction is larger than 0. Because otherwise this thing will be 0. You evaluate lots of things, and then you multiply it with 0, so you just counted half of the things 0. So I can immediately make this thing twice as fast that I had by just avoiding sending those rays that later on will be multiplied by 0. But I then have to divide by the probability of doing this, and when I make it more likely to go up, I then have to divide by this cosine term to get this division by P correctly. Yeah? And what you ultimately want, what everybody is after, and I will not go into detail with this, is product importance sampling. So what I did now is just to say if any of these factors is high, that's a necessary condition for the entire product being high. But ultimately, you want something where all of them are high, and then you want to send your rays there to discover the important structures. And we won't do this. But there are ways to do this, and they are very interesting and very, very advanced, but no, can't do now. I'll just show an example, then you can maybe ask about importance sampling. So here's somebody importance sampled for the light. And that was something that was for a long time not what people had been doing, but then it came out, and it's like maybe 10 or 15 years ago. And that's like now a very complicated light source. It's somebody captured the lighting configuration in a room, and then he put this virtual object there. And that's the same number of rays. It's almost the same time, I think. But here you see the variance is much higher, because here the rays were very often sent into directions where there was no light. So they just made a lot of effort to trace rays to then find out it's 0. And here it was already directing itself. So to find out, yeah, here maybe go in that direction because there is light. And then you get like a non-trivial contribution. And the variance is much lower. Of course, you have to divide properly and set up the math. But doing this is really feasible. And yeah, I think we agree that this is a better image. So question on importance sampling. Yeah? Yeah.
It's guided by probability of
Yes. Yes. This means if something is very unlikely, so you didn't go there very often, but you still find something, you have to count it more. Whereas if you always keep going somewhere, you will always find the high contribution, so you have to weight it down. So it's the opposite of the same thing. Yeah. And before it was n, where it's 1 over n. So if you take a uniform distribution, you just divide because it's the same everywhere. And here you just give different weights to them. But P is really the distribution of your omega I. So what would not work if you just either take a non-uniform distribution of samples and you don't divide by P, or you take a uniform distribution and you divide by some other P. They have to go hand in hand. Yeah? If you send more rays in that direction, you have to divide them more, but then you also have to send more. You cannot send them in all directions and divide more. It has to go hand in hand. They have to really work together.
Before it was divided by n,
Yeah.
divided by 1 over n.
Yeah.
And if P is 1 over n, then it will be divided by 1 over n.
No. Uniform distribution, this is just, you have to divide more where it's more likely.
Yeah.
So P is high, you divide more. This much I'm sure. I don't know what's your other consternation, but if you just have something and you see the same thing many, many more times, you have to just divide by more. This much I know. And, yeah. I will build it also into the code, then we will see. Maybe it's wrong, but I think this is the right way of saying it. And like really doing it, yeah, I said. So this is something that I had to do in my courses, like important sample for this one, and important sampling for the others. Yeah, it can be very hard. So rendering and solving integral equation, I think I said many times. Analytic and some numeric methods are not feasible. This time I didn't only explain like what you should do, but I also tried to explain why. I think that got clear maybe. And in Monte Carlo is the method of choice. Why? Because high dimensionality, no aliasing, and it even has some relation of how your retina is organized. Of course, it suffers from noise. The images you saw before, they're not noisy, but as we said, maybe you can just image blur, or you can just let it run longer. No free lunch. This will be a bit slower, but then it really converges to the right things. And besides waiting longer, there's another way of getting the variance down. One of them is choosing the right sample patterns that doesn't have holes, but still work in high dimensions. And the other thing is important sampling, where you make sure that you send more rays where the value of your integrand is higher. So this sounds like as if it is a complete solution, but I will show you just an example of why this is not. So maybe in the background, oh no, it wasn't rendering. Okay. So if you go here again, this is this thing, and this one doesn't come out really so well, yeah? And this is because if you really only start at the I ray, the probability, so to say, to find your way back to the light, imagine you sit somewhere, there are many, many ways you can go all the time, and every time it's an opportunity of not finding any light. So the other symmetric approach that you could take is, instead of starting to send random lights, random rays from the camera and try to find your way to the light, which might be very hard. If I put a light source here, I mean, come on, you will have to, it's very hard to find it, yeah? The other way, symmetrically, you can define the entire thing by just starting at the light and then hope that you will find the camera. It can also be unlikely. If I go somewhere where I really don't see stuff, then you have the same problem. But in some configuration, it's easier to start with the light. And ultimately, there are ways to maybe start at both and connect them in some way. And yeah, these are all the methods that are around photon mapping. So instead of sending something, I don't know what it is, from the eye, you start to send something from the light source and you connect it to the sensor. Much of the theory will still apply, but there are some little theoretical things you need to overcome. So I will explain to you photon mapping. I think it will take 1 hour. It's another generalization that can do this well. And then this will turn out also to have less variance. And there is even, I lack the time now, but if I set this to 4, this is 3 now. 1, 2, 3. If I set it to 4, you will, after some time, start to see some noise here. And that's acoustic. That's a light path that from here went to specular and then to diffuse and then to the eye. And these are very hard to find, because then you have to find exactly a configuration such that you see something in the mirror and then you see the light. So there are 2 ways that it can do wrong. So you roll 2 dice and you have to hope that both exactly form an angle such that the light is being simulated in this way. So then this will be really missing. But if you start at the light, chances are much higher. So this little caustic that here would be noisy, this is what you can do in photon mapping. That's what we're going to do on Monday. Yeah? Thank you. I have to check again. I'm not sure. Good. Why do you think it's...